if we take a gradient-based approach to solve this optimization problem, we would need to provide the gradients of the objective function. So let us see what those gradients would look like. For the first two random variables, x1 and x2, they are straightforward. We have already looked at them in problem C1 earlier in this lecture. So the partial of r with respect to x1, r being the objective function and x1 is the first decision variable, that would be twice u1 times the PDF of x1 over the standard normal PDF of u1. How does that come? We use the chain rule of differentiation. So we first take the derivative of r in terms of u1 and then u1 with respect to x1. There we employ the full distribution transformation relation between u1 and x1. So phi, capital Phi of u1 is equal to capital F of x1. So partial derivative of that with respect to x1 would give me small phi of u1 times partial u1 partial x1, and on the right hand side it is the PDF of x1. So that gives me this final form as twice u1 f of x1 over phi of u1, and this is also valid for x2 and u2 because they are mutually independent of all the rest. Now for x3 and x4, we need to take into account that there is a dependent structure. So let's proceed step by step. So partial of r with respect to x3 is now involves both u3 and u4 because they are related, as we saw in the previous slide. So partial u3 with respect to x3 and partial u4 with respect to x3. There would be some terms which do not count and some which do, because u3 and u4 we can now write in terms of the y's, the y3 and y4, those intermediate variables. So we see that the first set partial u3 with respect to partial x3 that has the y3 term coming from the linear relationship we saw in the previous slide, and the second term partial u4 with respect to x3 that also has a partial y3 contribution. So there now we have partial y3 with respect to x3 occurring twice. And just like we did for x1 and x2, the partial of y with respect to the x, we will use the same full distribution transformation information, and that gives me the ratio of the density functions. So the PDF of x3 over the PDF of y3. y3 and y4 are both standard normals. And that lets us express the partial of r with respect to x3 in terms of C11 inverse, C21 inverse, u3 and u4, and the ratio of the two density functions. And if we want to express y3 in terms of u3 and u4, we can do that, and that closes the entire expression. So we now have partial of r with respect to x3 in terms of u3, u4, and the density function of x3. Likewise, we can derive a similar expression for the partial of r with respect to x4. There we have the density of x4 and again u3 and u4 coming together. The gradients of the constraint, if they're useful, they are very simple because the constraint is a very simple function of x1, x2, x3, and x4. And if we again employ the MATLAB program, for example, fmincon that we used for problem C1, we would get the solution. And I'm just presenting the solution here. If you would like, you may want to write the code yourself and compare the results with what you see here. The minimum distance points in U space for the yield is about 1.4 times the standard deviation below the mean. For the cross-sectional area, it's also about 60% standard deviation below the mean. For the loads, they are above the mean. The dead load is almost at the mean. So the minimum distance point, beta, the reliability index, is 1.89, and the corresponding design values, the checking point values in the basic variable space is what you see on the screen. About 30 ksi for yield, about 56 square inch for area, about 1463 kip for the live load, which is less than what we saw in problem C1, and the dead load is slightly above the mean at about 206 kip. Now, we might be interested to know, and this is obviously a good question, as to what would happen if we did not take the trouble of going through this Native transformation. We did that because we wanted to be true to the dependence information that was provided, that correlation coefficient between D and Q. But what if we employed naively the Hasofer-Lind or the full distribution transformation, where in the first case the Hasofer-Lind is not even able to preserve all the probabilistic information in the transformation, and the full distribution, while it can preserve the probabilistic information for each variable, it cannot incorporate any dependence information. So here would be the results. Our beta comes to about 1.93. What we had before in the native was 1.89. So just a little bit overestimation of the reliability. The design values are roughly very similar as we stated in the previous slide. If you compare to the mean values, you see that Y and A are below the mean, D and Q are above the mean, D is slightly above the mean. If we went one step better from Hasofer-Lind, we employed the full distribution type transformation, then the result hardly changes. Beta comes down from 1.93 to 1.90, so it gets closer to the native result. The design values are roughly around the same, in the same region. And just to recap, what we got for the native was a beta of 1.89, and we have already discussed the design point values. Now, how do they compare with the true value? If we can find the true value, and hoping that Monte Carlo simulations gives the right result, backed by the law of large numbers, we have also solved this by Monte Carlo simulations, and the result is a slightly lower reliability at 1.77. So if that 1.77 value is right for reliability index, then native is definitely closer to that compared to Hasofer-Lind and full distribution. But this was a simple problem. The limit state was very well behaved. It did not have any inflection point. It did not have the curvature changing drastically. So we see that the three transformations, Hasofer-Lind, full distribution, and native, roughly giving very, very close results. Now, the Monte Carlo simulation is lower than that, gives a lower reliability. So again, here FORM overestimated reliability. One final point to note, and this is in favor of FORM type approaches, is that the Monte Carlo simulation can give us an equivalent beta, but it cannot give us the design point. So if we wanted a kind of intuitive understanding of what are the most likely points or what sort of design value we should aim for, then Monte Carlo simulation directly will not be able to provide that information.